All right, here we go with our third and final section of the unit 12.3, which talks about geometric sequences. Let's start off with this first sequence. Here I give you the sequence 8, 4, 2, 1, and I want you to find the explicit definition and the recursive definition. Go ahead and pause the video. Try this on your own. Quick hint for the explicit definition, try to model it using a function. All right, so go ahead and pause the video. Give it a try now. So in order to model this using a function, we first have to start off with a couple of points. We know that the first term in the sequence is 8, so we can define the point 1, 8. We know the second term in the sequence is 4, so we can define the point 2, 4. You may recognize that the rate of change here is multiplicative. We're looking at an exponential function, particularly exponential decay. So this can be modeled using the form y equals a times b to the x. So using our points, we can form two different equations. We have 8 equals a times b to the 1, and we have 4 equals ab squared. From there, we can solve this system of equations using substitution. I'll solve for a. So we have a equals 8 over b, and a equals 4 over b squared. We set them equal to one another. 8 over b equals 4 over b squared. Cross multiply, we have 8b equals 8b squared equals 4b. Subtracting the 4b from both sides, we have 8b squared minus 4b equals 0. We'll factor out a 4b, so we have 2b minus 1. And then using the zero product property, we find solutions b equals 0, b equals 1/2. Now, which solution do we choose? Well, we know that this is an exponential function, so we have to eliminate b equals 0. Remember, b is the growth or decay factor. It can either be between 0 and 1, non-inclusive, or greater than 1. If it is 1, then it's a linear function. It's actually a constant function. So we choose b equals 1/2. If we plug it back into either one of these equations, b equals 1/2, we can solve for a. We find that a equals 16. So then we can say that the sequence is defined by an equals 16a, and then b is 1/2 to the n. How can we find the recursive definition? So as a reminder, the recursive definition means that for any given term, it's determined by one or more of the previous terms. So we're saying that what happens each time, let's look back up. What happens each time? We're dividing by 2 each time, right? So for any given term in the sequence, it is half of the previous term. So our recursive definition could be for an, we have an minus 1, the previous term, over 2. We divide it by 2. All right. This brings us to geometric sequences. Let's define what is a geometric sequence. A geometric sequence is a sequence in the form, so that's going to be in the form AR squared, AR cubed, and so on. So what are A and R? Well, where A is the first term and R is the common ratio. So just like in arithmetic sequences where we have D is the common difference, in geometric sequences, because the rate of change is multiplicative, R represents the common ratio between each term. So what happens between each term? Well, from A to AR, we multiply by R. From AR to AR squared, we multiply by R. From AR squared to AR cubed, we multiply by R. So that common ratio between each successive term is R, the common ratio. r is the common ratio of the sequence. The nth term of the sequence, so the nth term of a geometric sequence, is given by, so we'll say an equals, well, let's see if we can come up with the pattern. We have each successive term is multiplied by r. We know that the first term is a. So if we're modeling this using an exponential function, we can say that it's our initial value a, our multiplicative rate of change is r to the n. But that's not quite right. Our first term doesn't have an r, so it's got to be r to the 0. So for the first term, n equals 1, we have to shift it over 1. So our first term is going to be just a, and then our second term is going to be r to the 1. And then our third term is going to be r to the 2. So it's all of the n minus 1. All right. Example 1. Find the first 5 terms of the geometric sequence where letter a, or a equals 3, and r equals 2. So this here, again, we've got the general form an equals a times r to the n minus 1. So plugging in, we want the first term, a1, is going to be a, which is 3. Why don't I write 3? Which is 3 times r, which is 2, to the n minus 1, so 1 minus 1, or to 0. And that's just 3. So we have 3 times 1 is 3. A2 is going to be 3 times 2 to the 2 minus 1, or 2 to the 1, or 3 times 2 gives us 6. A3 is going to be 3 times 2 to the 3 minus 1 is 2. Gives us 3 times 4 is 12. A4, well, again, our rate of change is multiplicative. We're multiplying by 2 every time. So 3, 6, 12. The next one's going to be 24. And the fifth term is going to be 48. Go ahead and try letter B on your own. Pause the video and check your answers in a few moments. All right, here's the letter B. A couple things I want to point out. For A1, we know that it's 1 because we're given A equals 1. Remember, A equals 1 tells us our first term in the geometric sequence. So there's no arithmetic required for A1. We know that it's equal to 1. Also, you may notice that every successive term flips from positive to negative, and from negative to positive to negative, and so on. We get this from a negative r, right? So when we're taking, because it's r to the n minus 1, for every odd power, it's going to be positive. For every even power, it's going to be negative. All right, let's find the 8th term of the geometric sequence, defined here, 5, 15, 45. First things first, our first term is going to be a, which is just our first term, 5. Our r, so our rate of change, is going to be the ratio of 2 successive terms. 2 consecutive terms. So let's just choose the first 2 just for simplicity's sake. We're going to take the ratio of 15 and 5. And that gives us 3. So every time we're multiplying by 3. You can double check that with 45 divided by 15 should be 3. So to find the 8th term, we plug it into our general form. an equals a times r, which is 3, to the n minus 1. So 8 minus 1. So we have 5 times 3 to the 7th. Evaluate that in your calculator, you get 10,935. Next up, we've got the 3rd term of the geometric sequence. So A3 is 12, and the 6th term, A6, is 96. And I want the 11th term. So what do we know? How do we get from A3 to A6? Well, in a geometric sequence, every successive term is multiplied by the common ratio r. So in order to go 3 steps in this sequence, so from 3 to 6, we have to multiply by r 3 times. So we know that A6 is equal to A3 times r cubed, or r times r 3 times. So A6, which is 96, equals A3, 12, times R cubed. Divide both sides by 12, and we have R cubed equals 8, or R equals 2. Okay? And then, to find the 11th term, well, how many steps are we moving from A6 to get to the 11th term? That's 5 steps. So it's going to be A6 times R to the 5th, because we're multiplying by R 5 times. And that'll give us our 11th term. So 96 times R to the 5th equals A to the 11th, A11. And we know that R to the 5th is 2 to the 5th. So 96 times 2 to the 5th equals A11. And then evaluating, we have A11 equals 3072. Like all other sequences, let's talk about partial sums. So given the geometric sequence, and that sequence is defined by an equals ar times a times r to the n minus 1. The nth partial sum, and we can write out that partial sum, is capital Sn equals that first term plus the second term, ar, plus the third term, ar squared, plus ar cubed, plus all the way up to the nth term, which is ar to the n minus 1. And just note that r cannot equal 1. This partial sum is given by Sn equals a times 1 minus r to the n over 1 minus r. So let's find the partial sum of the first 10 terms in this sequence here, this geometric sequence. So here we have 2, negative 6, 18, negative 54. We know that a, our first term, is 2. What happens between each term? What are we multiplying by? So what's our common ratio? To get from 2 to negative 6, we multiply by negative 3. To get from negative 6 to positive 18, we multiply by negative 3. And to get from 18 to the negative 54, we multiply by negative 3. So our common ratio is negative 3. So plugging it in, we have S10, we want the 10th partial sum, is going to be a, which is 2, times 1 minus r, which is negative 3, to the n, which is 10, over 1 minus r, which is negative 3. We evaluate, we have 2 times 3 to the 10th is 59,049. So 1 minus that is going to be negative 59,048. And then 1 minus negative 3 is a positive 4. Evaluating this, we get negative 29,524. Another way you could find this is using sigma notation. So we have the sum of 2 times 3 to the, we're going to use k, our index, k minus 1, where k goes from 1 to 10. So you can also use sigma notation to evaluate this sum. Let's talk about infinite series. So a series is like a sum of a sequence, right? So if we add all these terms, 2 plus negative 6 plus 18 plus negative 54, that would be considered a series. An infinite series is a sum that goes on infinitely. So sigma all the way up to infinity or approaching infinity. We want to just continue that series on forever and ever. That's an infinite series. So let's talk about an example of an infinite series. So suppose you're given a cake and you want to eat it by first eating half of the cake, then eating half of what remains, and then again by eating half of what remains then, and so on and so on. So after the first serving, you've eaten half of the cake. After the second serving, you've eaten a half, and then half of what remains, that other half, so a fourth. So you've eaten a half and a fourth. You eat another half of what remains, and that means you're adding another half of a fourth, which is 1/8, and then you're eating another 1/16 and another 1/32, and so on, right? So we're talking about, you can do this infinitely, right? You can continually eat another half of what remains. Okay. So let's see if we can write out a partial sum Sn that represents the total amount of cake eaten after n servings. So Sn is equal to, well, after the first serving, you've eaten a half. After the second serving, you eat a fourth more. So you add a fourth. After the third serving, you eat an eighth, 16th, 1/32, and you can continue to do so all the way up to the nth serving, which would be 1 over, well, we have 2, 4, 8, 16, 32. These are powers of 2. So the nth serving is going to be 2 to the n. What happens to the total amount of cake eaten as you eat more and more servings? So in particular, how much of the cake have we eaten as the number of servings increases to infinity, right? We want to approach infinity. So what happens to Sn as n approaches infinity? Well, as n approaches infinity, as we eat more and more servings, what happens to Sn? Is it approaching some number, right? We can't ever eat more than one whole cake, right? We get closer and closer to eating the whole cake, but there's still a tiny little sliver left over every single time. So as n gets really, really big, we increase the number of servings. We approach this value. We approach 1, right? As you eat more servings, you get closer to eating an entire cake. Given here, we have the series Sn equals 1 plus 2 plus 4 plus 8 plus 16, and so on, where this should be minus 1. What happens as n approaches infinity? So we have, so go ahead and write this in. This is plus 2 times 2 to the n minus 1. So what happens as n approaches infinity? Well, we have all of this gets bigger and bigger, right? So this continually increases 2 to the n minus 1. If n is really big, n minus 1 is still really, really big. 2 to a power that's huge is just, it's going to be huge. So as n approaches infinity, Sn is also approaching infinity. It's never going to meet at some number like this one does. It's just going to continue off getting bigger and bigger and bigger. No matter how big n gets, as you increase, Sn is also going to increase. And that brings us to the sum of an infinite geometric series. So, given the infinite geometric series, and I'll go ahead and write that, so sigma, I'm going to use sigma notation, AR to the n minus 1, sorry, k, that should be k, where k starts at 1 and goes off into infinity. So this is an infinite sum because we're taking the sum of infinitely many terms. So writing this out, this would be a plus ar squared plus ar cubed, and so on. That continues infinitely. This series, we say, converges if the absolute value of r, or the absolute value of our common ratio, is less than 1. Right, so in that cake example, we approached a number. We approached 1 as n goes off into infinity. We're saying that that series converges to 1. So the reason why that converges to 1 is because the multiplicative rate of change was 1/2. We're eating half of the cake every time. So that's less than 1. The sum of this geometric series is S equals, so the sum equals A over 1 minus R. If the absolute value of r is greater than or equal to 1, it doesn't converge, it diverges. So this geometric series diverges if r is greater than or equal to 1. Let's try a couple of examples. Here I've given you two series, and I want to know if they converge or diverge, and then if it converges, what does it converge to? So looking at this first one, really what we need to know, whether or not it converges or diverges, is we need to know about R. So let's find R. R is the ratio of two consecutive terms. So to find R, we're going to take just two consecutive terms. I'm going to choose the first two, so 33 tenths over 3. If we simplify that fraction, 33 tenths divided by 3 gives us 11 tenths. Well, since the absolute value of 11 tenths is greater than 1, the series diverges. Let's take a look at letter B. So again, we need to talk about R. So R is the ratio of consecutive terms. We have 5.6 over 7. I'm choosing the first two. If we evaluate that, we get 0.8. Well, that's less than 1. So since the absolute value of 0.8 is less than 1, the series converges. And we got to know, what does it converge to? So let's plug it in and see. S equals A. Well, A is our first term. So A is our first term, 7. So 7 over 1 minus R. R is 0.8. So evaluating this, we have 7 over 0.2, which is 7 times 5 is 35. So this converges to 35.